Can you hear me? How's the volume on this? Good. Okay. Cool. So let's get started. My name is Ray Sharma. I'm a graduate student at Rutgers University, working with Allison Brooks on the ROMULUS suite of simulations. And in particular, I want to look at the black holes in Romulus's dwarf galaxies. And before I actually start talking about black holes, I want to go over what Romulus is. So the Romulus suite of simulations is primarily made up of two volumes. We have the Romulus 25 megaparsec volume, and then a zoom-in of a galaxy cluster. This is Romulus C. Michael Tremmel will be talking about this. I'm going to be focusing on the 25 megaparsec volume. And one of the main draws for Romulus is our ability to create certified organic, free-range, locally grown SMBHs. And what I mean by this is that we have self-consistent and physically motivated dynamics, growth, and feedback stemming from our treatment of black holes. More on this later. So for the specifics of Romulus 25, we inherit all of our standard physics from gasoline. The main difference really comes in our black hole physics. And on the right, we have an image, a pretty standard image of a low-mass galaxy. These are the kinds of objects that I'm going to be talking about. And so the physics is covered in more detail in this paper, Tremmel 2017, but we have the same prescriptions for star formation, our cosmic UV background, metal cooling, blast wave supernova feedback. That's all inherited from gasoline. So then what do we do differently in Romulus? Well, we include a subgrid prescription for dynamical friction on scales below our spatial resolution. And we also include a modified Bondi-Hoyle accretion prescription, which includes angular momentum support. And then finally, we have a seeding mechanism for our black holes that is physically motivated. And it's actually built, it's some version of direct collapse. And we heard about the different modes of seeding earlier, so this is kind of like the direct collapse model. So for the actual seeding itself, we seed all of our black holes at a mass of 10 to the 6th, and the actual seeding itself is tied directly to the environment. So rather than placing black holes, we seed black holes based entirely on properties of the environment that the gas is sitting in. And so if the gas is metal poor, if it's very high density, and if the temperature is something like 10 to the 4 Kelvin, you have the conditions required to seed a black hole. And what we find is that the majority of black holes that are seeded in Romulus are seeded within the first gig year of the simulation. So then moving on to actual observations of black holes, I'm going to be showing this relation quite a bit. So what I have plotted here is the black hole mass versus stellar mass relation from Shaman-Silverman 2013. And notice that the data points go down to something like 10 to the 9.8 solar masses. So when I recreate this plot using our data, Romulus is unique in that our black holes can be seeded in dwarf galaxies down to masses as low as, well, lower than 10 to the 8, but I only have plotted here down to 10 to the 8 solar masses. And so plotted in black here are all of the galaxies in Romulus 25 that contain black holes. Plotted in blue are the galaxies that are isolated field galaxies. And so I do this to separate out effects of the environment so I can look at what black holes are able to do to their galaxies even at these low masses. And so what you can see here is that we follow the relation at these fairly high masses, and then we have galaxies below the observed relation. And what I really want to focus on are these galaxies just below the observed relation. This is like a good sample for us to look for properties, properties of the galaxy that the black hole might be able to affect, and perhaps extend, to create predictions like for galaxies just below this observed relation. So one thing that we're able to do in Romulus is to track the growth histories for the black holes and for their host galaxies. And so what I have plotted here are those same galaxies that I had boxed over here, just the isolated galaxies. And what I find is that the early merger history of the black hole seems to matter. What I can do is actually look at the tracks for black holes that are considered overmassive. These are just black holes that fall above the extrapolated observed relation. And we find that these black holes tend to undergo early mergers with other, like black hole mergers at early times, and this seems to influence where they fall in regards to the observed relation. And so moving on to the structure of the galaxy and how it changes with the presence of a black hole, what I have plotted here is the size-mass relation for galaxies with black holes, which are plotted in orange, and then without black holes, which are plotted in blue. And what we find is that at certain stellar masses, there seems to be a difference in the effective radius of a galaxy just based on whether there's a black hole present in there. And so looking at the sample that I highlighted earlier, we don't see much of a change in the effective radius. The colors are the same here. Orange is with black holes, blue is without black holes. We don't see much of a change in the effective radius in this mass range. However, if we were to look at a lower mass range, there does seem to be some sort of systematic difference in the effective radii based on the presence of a black hole in this galaxy, in these galaxies. Okay, and then we can move on and look at, say, the and we can make this statement that having a black hole seems to give you a higher effective radius at lower masses. So we can move on to looking at the gas fraction. And so when I say gas fraction, I'm looking at the H1 gas fraction. And so plotted on the y-axis is the gas fraction, and then on the x-axis is the stellar mass as usual. And what we find is that there doesn't seem to be much of a relationship between the presence of a black hole and the gas fraction. So having a black hole doesn't actually seem to change the total gas fraction of a galaxy. So we can say that having a black hole does not really seem to change the gas fraction. Now, the third structural property that I looked at had to do with the central density. And so what I have plotted on the y-axis here is the surface density of stars within the inner kiloparsec of the galaxy. And I have this plotted against the stellar mass. And what we find is that there's a systematic shift between galaxies that have black holes and do not have black holes, and that those that do have black holes tend to have lower central densities. We reproduce the observed relations, but what was really interesting is that having a black hole tends to lower your central density. And so this relationship still applies in this mass range that I highlighted earlier. And so to summarize, Romulus is uniquely capable of tracking both black holes because of our seeding mechanism. We're able to track them as soon as they're seeded, and also track low-mass galaxies because of our high resolution. And Romulus, in this way, is capable of making predictions. So we've seen that the presence of a black hole in dwarf galaxies seems to affect the dwarf galaxy. We've seen that black holes can increase the effective radius of galaxies at least low masses. The presence of a black hole doesn't seem to change the gas fraction, at least at these lower masses. And black holes tend to decrease your central density at these lower masses. And there's a paper in preparation with more of these kinds of results, so stay tuned. Thank you.
Thank you very much. We have one question here.
So have you thought about how black holes change the size of dwarfs? Given that they don't change the gas fraction significantly, so I don't assume the black holes just push the gas out and in, right? So what's the mechanism that changes size?
That's a good question. I mean, it could be tied to this. It could be tied to this, right? Like if you're seeing a, let's see, if you're seeing a lower central density, then you are seeing, then presumably those stars have to go somewhere, right? So if those stars were, for whatever reason, at higher radii, then you'd see a higher effective radius. But I don't know the mechanism by which that might happen.
Other questions?
Yeah, slightly more detail. It's covered in the paper, but it's fine. So when we include angular momentum support, essentially like our black hole accretion rate now has like a velocity term that like a, what would it be? Like a rotational velocity term, as unusual. Yeah, it's covered in the paper. No, I don't think we. Do we?
We do cap it, but they're always quite low at its ratio of the system. So very rarely, especially at Dwarfs, but even in the Galaxies, rarely.
Okay, let's take a last question while Matilde prepares her computer.
I was wondering whether you included any sort of scouring effect in your models, and if so, does that make any difference for the dwarfs?
Sorry, what was that?
Scouring, where the black hole, causes the change the orbits of the stars, and therefore redistributes them in the central regions of the galaxies.
Oh, that's a good question. Actually, I think Michael, your paper, the 2017 paper had that binaries. Is that right?
No, so we don't follow binary evolution, right? So scouring will happen if you actually have a binary black hole on a parsec scale distance, which is well below our resolution. We don't follow the dynamics. That I didn't take into account. It is possible. Is the black hole sinks by itself? That maybe hasn't.
Let's thank Rai again. And next talk is Matilde Minga.